Hi guys, John the Quant here. This is week 6 of the free data science bootcamp that I'm presenting to you guys, and I also guide at the Community College of Aurora. Now, if you're wondering, week 6, hasn't it been like 10 weeks? Well, I've been sick for the last couple of weeks. My voice has just come back, so we're getting right back into it. Last week, we learned all about the different kinds of models that you can fit, and this week, what we're learning about is how to fit a good model. We're going to treat this as a 3-step process, and that's why there are 3 videos. This video is all about baselines. What is a baseline? Why would we want a baseline, and how do you work with baselines? So let's get into it.
So we're going to have a look at this both in classification and regression. We're using all of our normal packages. That's Pandas, NumPy, Matplotlib, and Seaborn. And then down here, we're doing both classification and regression. So for classification, we've got our transformed diabetes data that we're pretty familiar with already. Here's our outcome. It's either 0 or 1, and it should be a category. And then for regression, I'm using the data science salaries data that we used in a mini project, a few weeks ago, I guess. So this has not been transformed at all. We're just going to use the raw data for this. Our target column is going to be salary in US dollars when it comes down to it. So the first thing that I want to do most of the time is just immediately go into train test split. So I'm using scikit-learn, the train test split function from the model selection subcategory there. And we're splitting it with 80% training data. Now, when we're fitting a model, particularly a good one, you pretty much always want to start with a baseline, okay? In the real world, we can calculate accuracy and we can calculate RMSE or whatever other metrics we want, but those numbers are really meaningless, okay? So, like, if a model has 66% recall, is that good? We don't know. I mean, we don't even know if 100% is good, because we can always get 100% perfect recall by predicting the positive class every time. So, like, if we just predict that everybody has diabetes, that is 100% recall, and we still don't know if it's good. So what we need is some metric to compare the other metrics to, and that's what a baseline is going to give us, okay? A baseline is a simple model that gives us something to compare our other models to. There are quite a few ways to design baselines, and the best option usually depends on a whole bunch of different things, like what is your goal, what kind of problem is this, and different things about your data set. So we're going to split it into classification and regression, and we're going to look at a few common baselines. The classification problem, right, is where you're trying to decide which class or group each observation belongs to, and the output is categorical. Okay, people either have diabetes or they don't. It's categorical. So the most common baselines for this are majority class baseline. Okay, so that means just predict that every observation is the most common category. And this is really useful when the classes are highly imbalanced. Say if like 95% of people don't have diabetes, only 5% of people do have diabetes, then your model is going to be 95% accurate if you just predict that nobody has diabetes, okay? A highly imbalanced data set can have metrics that look very good just by using the majority class baseline. So that's why we want to use this, is we want to know how good can we do without building a model at all. The next common baseline is the majority random baseline. So in this case, the uniform random baseline. So in this case, we'll randomly assign each observation to a group, with each group being equally likely. Okay, this baseline makes the assumption that there is no useful information in the data. And since we have no information that might help us predict which class each observation falls into, we're just going to guess randomly. And this baseline is helpful when you're really not sure if there's any hope of actually making good predictions, like when you're prototyping a completely new idea. I used this one personally at my last job. The situation was I was trying to predict how likely a customer was to use the platform within the next month. And I had them split into 4 different classes of probability, and I really wasn't sure if anything that I was going to do was going to make any difference. If I didn't know if it was predictable at all. So I compared it to a uniform random baseline. I was able to improve on it significantly. And that's how I was able to like sell my ideas there. So uniform random baseline is good for prototyping, or when you just don't think for when you suspect that you might not actually be able to improve upon randomly guessing. All right, next is the proportional random baseline. This is similar to the uniform one, because we're randomly assigning each observation to a class, but instead of doing it uniformly, where each class is equally likely, in this case, we're going to say that the probability is determined by the proportion of that class in the training data. So, in my example for majority class baseline, I said that like 95% of people don't have diabetes, right? So if we wanted to do a proportional random baseline for that, we would randomly assign people to not have diabetes. We would randomly assign 95% of people to not have diabetes and randomly assign 5% of people to have diabetes, and that would form a proportional random baseline. All right, so when all of the categories have the same number of observations in the training data, the proportional random baseline and the uniform random baseline are exactly the same. The last baseline that's common for classification problems is a constant baseline. So in this case, we just predict that every observation is whatever class you want. All right, like imagine, say 95% of people don't have diabetes and 5% of people do, but you want to see what would happen if we just predict that everybody has diabetes, right? So if we just treated everyone for diabetes, would that be a good thing? So in that case, you could use a constant baseline to predict that everybody has diabetes and just see how that goes. Another example that I give here is if a telecom company will make more money by just giving every customer a 10% discount rather than by targeting certain customers, like why bother even making a churn model? So that's really the question that a constant baseline asks, right? Is there even a point to making a model at all, or should we just assume that everybody falls into one group or another? All right, let's go ahead and make them. Majority class baseline. Remember, this is where we predict that everybody is in the most common class. So to do this by hand, I have a list comprehension here. If you're not sure what that means, go ahead and Google it. So I'm going into the class train data frame, the training data, getting the outcome, which is the target feature, and then using the dot mode, and then value 0. So this is going to give me the most common class. All right, and then I'm just using this times the test shape. So just predicting that everybody's in the most common class. But scikit-learn has this great dummy classifier object. So from sklearn.dummy, import dummy classifier, and we can actually make all 4 of our baselines using this dummy classifier. So our model here is then a dummy classifier with the strategy being most frequent, because this is the majority class baseline, most frequent. And then you can fit it on the training data. It doesn't actually learn anything other than which outcome is most likely. And then to get the predictions, you use the majority class model.predict on the test data. And it's going to predict that everybody is in the majority class. Next, fitting a uniform random baseline. You can do this by hand using numpy.random.choice and getting the... So I'm choosing from the unique values of the outcome, and I'm just choosing the same number as the test size. But the dummy classifier can do this too. So in this case, it's dummy classifier with the strategy equals uniform random baseline, uniform there. And when we fit it, it's just going to calculate the probabilities, really. But you fit it just like any other model, and you use the prediction just like any other model, and that's just going to randomly assign observations to each class with the same probability. Next, the proportional random baseline. You can do this by hand, although it is a little more complicated. First, you have to get the proportions, which you can do by using the value counts on the series on the target feature, and divide that by the number of training observations. And then you can use, again, np.random.choice. And so here I've got outcome proportions.index. This is all possible classes. Then the size is the size of the test shape. Size of the test data set. There we go. And then the probability is the proportions that we calculated up here. Or the dummy classifier can do it. So if you use a dummy classifier with the strategy equals stratified, then when you fit that on the training data, it is just going to get the probability of being assigned to each class, and then when you do predict, it is going to assign observations to each class based on the probability, based on the proportion of that class from the training data. Lastly, constant baseline. I tried both 0 and 1. So here, by hand, you just create a new column and assign it to 0, or assign it to 1. That's it. Very simple. Now with scikit-learn, you can do this as well. Dummy classifier, strategy equals constant, and then you have to tell it what constant to do. So this is where the constant is equal to 0. You fit it like normal. You predict with it like normal, and it just returns 0 every time. Or down here, dummy classifier with the strategy equals constant and constant equals 1. So then you fit it like normal, and when you predict with it, it's just going to return 1 every time. And now we're looking at the baselines here. Right. This is our proportion of predicted zeros. So more people don't have diabetes than do have it. So 100% of our predictions from the majority class baselines are zeros. 100%. And then when we did the uniform random baseline, well, when we did it by hand, 46% of our predictions were zeros and 53% of our predictions were ones. And when we did it with scikit-learn, about 53% of our predictions were zeros and 47% were ones. Okay, both close to 50-50 because it's uniform. Now when we did it proportionally, by hand, about 75% of our predictions were zeros and 25% were ones. And then when we did it with scikit-learn, it was about 69% and 31%. And that's the biggest difference between the two, by hand and by scikit-learn, which is pretty interesting. So when we did constant 0 baseline by hand, 100% of predictions are zeros. Constant 1 baseline by hand, 100% of predictions are ones. Constant 0 baseline with scikit-learn, 100% are zeros. Constant from scikit-learn with 100% were ones. And this is our original proportions. Originally it was 64% zeros and about 36% ones. So right here, the proportional random one from scikit-learn was actually closer to being the same proportionality as the one we did by hand. So there's our baselines. We're looking at this to see how similar is this actually to the original data. All right, so if I was really doing this, the most reasonable one probably seems to be the proportional random baseline from scikit-learn. Seems like that is probably the best baseline, but it doesn't really matter. You can learn something important from every single one of these. Now, how do we actually use these? Well, a baseline gives you something to compare your model to. So once you've got a baseline, or more than one, it's okay to have 9 baselines, however many we did here. Okay, you fit a model, and you calculate metrics on both your fitted model and the baselines, and hopefully your model is like a lot better than the baseline. So here, we're going to use a random forest classifier from scikit-learn, and I'm just fitting that on the trained data and predicting using the test data. Now we're going to look at some metrics here. So I'm making a whole bunch of classification reports. It doesn't like this because we've got, here the majority class baseline had 0 predicted ones, so it's giving us all these warnings saying you have no predictions in this class. But it doesn't matter, okay? So majority class by hand, our accuracy was 68. You can see our precision and recall for zeros was okay, I guess. 100% recall. But since we never predicted a 1, we get zeros across the board there. Our majority class from scikit-learn is exactly the same. When we did the uniform random baseline by hand, we ended up with 43 and 47% recall, with zeros and ones respectively, 44% accuracy. So this was actually less accurate than just predicting that everything was a 0. Uniform from scikit-learn did a little better, with 52% accuracy, although, how much does this really matter, right? And then the proportional random baselines, 60% accuracy by hand, 75% and 27% recall. So the recall is not actually very good. Down here, the recall looks a little better to me, the proportional random one from scikit-learn, even though the accuracy has gone down. The recall for zeros is 71, not that big a difference. The recall for ones has gone up to 35, which is definitely much better, much closer to what we really want. Now, the constant zero baseline is actually exactly the same as the majority class baseline. And the constant 1 baseline is sort of flipped, the opposite. We had only 32% accuracy, but now we've got perfect 100% recall on the positive class. So we're capturing everybody that has diabetes by just guessing that everybody has diabetes. And it goes on like this. And then the random forest classifier, which we're hoping does much better than any of the baselines, has 77% accuracy, which is already a lot better than our best baseline, which was 68%. And then here at recall, for zeros, we've got 83% and 63%. And these are much better recall numbers than any of our baselines was able to give us. So we've definitely improved on the models by using a random forest classifier instead of any of our baselines. But we wouldn't know that we had improved anything by using a random forest classifier unless we had looked at all of these baselines. So now, same thing, but now we're looking at confusion matrices. And again, on a confusion matrix, what you want to see is that almost all of the observations are on the diagonal, and that everything that's not on the diagonal is close to the same. So here, we've got a lot of observations that are not on the diagonal, and the diagonal is not balanced, so we know that this model has a lot of problems. Which, of course, it does. It's just a majority class baseline. Starting to look a little better, I guess, but now we're getting a whole bunch of false positives, right, with the uniform random models. Same here again. And here we're getting these large, from the proportional random models, we're getting a lot of observations off the diagonal. Even though the ones off the diagonal are pretty well balanced, we're still getting a lot of them off the diagonal, which is not what we want. Now we'll look at the random forest, and we'll see that most of the observations are on the diagonal, and everything that's not on the diagonal is pretty balanced. So this also tells us that the random forest classifier is a better model than any of the baselines. Okay, to continue on here, we're looking now at the AUC. This is the area under the curve of the, I think it's the receiver operating characteristic. Receiver operating curve, maybe. ROC. I'll look it up. Now, the way that this chart works is there is a line at a 45-degree angle down the middle, and if you guess randomly, if you're pretty much random, then your model will perform on this line. So you want to do better than the line. You want your model to be out here. So this tells us this is just like random guessing. This is kind of like random guessing. This is worse. This is worse than, just doing something at random. And here, we're getting slightly better. But none of these baselines are really outperforming that straight dashed line. But the random forest clearly is. Its line is way out here, way off of the dashed line. So that tells us, once again, that the random forest classifier is better than any of our baselines. So now let's look at regression baselines. And once again, there's a whole bunch of them, and there's a dummy regressor class from scikit-learn. The big ones, though, are the mean baseline, where you just predict the mean value of the target, okay, and that's most often used when the target column, is expected to be symmetrical. You can use a median baseline, where you're just predicting the median value of the target, and that's most often used when the target column is not expected to be symmetrical. You can use a quantile baseline, which is where you predict a certain quantile of the target, and this is often used to evaluate the decision-making power of predictions. Okay, it's kind of like a constant baseline for classification, where you can say, if people are, what if we just predict that everybody is like in the bottom 25%? Like, what happens if we just predict that all data science salaries are in the bottom 25% of data science salaries? There's also a constant baseline where you predict a constant value, and once again, it is used to evaluate the decision-making power of predictions. Like, what if we just predict that all data scientists get paid $100,000? What would that do to our decision-making process further down the line? All right. Now here, we're not doing any of these by hand. We're just using the dummy regressor. So from scikit-learn.dummy, import the dummy regressor. And here, for the mean baseline, you use strategy equals mean. And I'm fitting that on the training data to predict the salary in US dollars. And then we're using it to predict just like a normal model. Same thing here for the median baseline, but we're using strategy equals median, fit it like normal, and predict with it like normal. For quantile, using dummy regressor with the strategy equals quantile, and here I'm predicting everybody is at the 25th percentile. Everybody makes the same amount of money as the 25th lowest paid person. All right? And then we're just going to fit it like normal and predict with it like normal. And then constant baseline here, strategy equals constant, and I've used $100,000, and you fit it like normal and predict with it like normal. And now we can see what this is doing. So this is the mean. This is the median. Now, if the mean is higher than the median, like it is here, that tells us that these are actually right skewed. So there are some data scientists that are getting paid a lot of money that moves the median further over. The mean. That move the mean further to the right. Okay? So this mean is slightly higher than most people actually make. The median is exactly where 50% of people make. The quantile this is exactly what 25% of people make, and then our constant 100,000. So scikit-learn's regression baselines, all of these are constant. They all just repeat all the time. Now you can make a more interesting baseline pretty easily. For example, instead of using the mean of the entire target column, you can group the data by a categorical column and then use the mean from each group, which is what I've done here. So I've got the training data and I'm grouping it by location and then taking the mean and getting the mean salary. So this is the mean salary by location. And then next I am filling it in here using the mean by location. And I've done the same thing with experience by doing group by experience level and taking the median salary in US dollars and then just assigning it to each observation in the test set. So now you can see that it varies. First by location, and then by then by experience level. Mean by location, median by experience level. I just kind of, made up a couple that kind of made sense to me so that we could see what these more interesting baselines do. Now we're using a baseline, so I'm going to compare it to a random forest regressor. I also need a one-hot encoder because our data up here is not pre-processed. So we need the one-hot encoder to handle all of these categorical columns, categorical features. All right, so I've fit it and transformed it using the one-hot encoder, and then fit a random forest regressor here. And done the same thing with the test set and got the predictions. Now we can compare some metrics. Metrics we're going to use here are the R2 score, which you can think of as the percent of variance explained. You should definitely Google that one because it's a pretty cool score and it's used a lot. We're also going to look at mean absolute error, mean squared error, the maximum error, and the Spearman correlation. And we'll talk a little bit more about this one whenever we look at that here in a minute. All right, so we're just calculating those by looping through all of the columns and calculating it for every one of our baselines. And down here we've got it. Our R2 score, you want this to be closer to 1. Closer to 1 is better. 1 means that it's predicting everything exactly perfect. Negative means like that it's worse than guessing, I guess. I don't know. Negative is bad, all right? You want it to be as close to 1 as possible. And you can see that our random forest regressor was actually way better when it comes to R2 score than anybody else. Skip correlation for a second. The mean absolute error, you want this to be smaller because it's an error. So these are all pretty big. You can see here 28,000 for the random forest is way lower than the second lowest, which is 41,000, which was mean by location. Mean squared error, again, you want this to be lower. These numbers are enormous, and they're really hard to understand. This one starts with a 1, so it's probably better, but I just wouldn't look at this anymore. All right, the root mean squared error, again, lower is better. The random forest at 38,000 is way lower than the second lowest, which was median by experience at 50,000. Then the maximum error, again, lower is better. Here, our random forest was 139,000 compared to the second lowest, which was median by experience level at 152,000. So all of these are actually telling us that the random forest does better than all the other models. Now, correlation, sorry, we're going to look at it graphically. We will talk about correlation. But if we look at this graphically, again, you can see that here you want it to be higher, and the random forest is clearly higher than everybody else. Correlation, you want this to be higher. Random forest clearly higher than everybody else. Mean absolute error, you want this to be lower. And the random forest is clearly lower than everybody else. It's clearly lower on mean squared error, clearly lower on root mean squared error, and clearly lower on max error, although these are actually getting a little bit close together. Okay, this is a prediction error display, okay? And this is nice for looking at correlation and determining how well your model is actually doing at predicting directionality. So here, when we're just using the mean, we're predicting the same value every time. So there's like no correlation or very little, and that makes sense. And then on this side, we're looking at residuals. So if you remember, okay, so what we want in this graph is we want our dots to be along this line, which these clearly are not. And then on this one, we want them all to be centered around 0. We want it to be about equally distributed above and below 0, and we want them to be centered around 0, and these clearly are not either. Same with this. And if you think about it, no constant model, like any of the dummy regressor baselines, is going to look good on these plots. But there are some things that you can kind of find out about them from looking at it this way. And here we go. When we finally get to mean by location, it looks like maybe there's a relationship here, but it's not a very good one. And these are definitely not equally distributed, and they're kind of all over the place. If we look at median, this is starting to look more like it actually is related to the dotted line, which is what we want. And it's maybe looking a little bit better, but not great. You can see these big swoops. This is a really low variance, this is really high variance, and so on. And now for our random forest, now we're really starting to see that there's a relationship between the predicted values and the actual values. Okay, it's kind of following the dotted line. If this was a perfect model, all of these dots would be exactly on the dashed line there. And then on the residuals, they're starting to look more spread out. And while it's still kind of, they call it trumpeting, because instead of being uniformly distributed around 0, it kind of grows like this. But it definitely looks more like a decent model. All right, let's go back to in person, and we'll talk about the next step in fitting a good model.
Well, there you go. Now you guys know all about baselines, why you need them, and how to work with them. In this week's mini project, you will be asked to choose and fit a baseline. Just use the scikit-learn baselines. That's what I would do. All right. Now the next step is to understand the hyperparameters of our model, and that video should be popping up down here in one of these two spots. I forget which. So if you guys learned something here, give me a thumbs up. If you have questions, leave them in the comments below. And if you see questions in the comments below, do your best to just add to the conversation down there. All right? It's all about us learning together. And if you want to keep learning with me, go ahead and subscribe. I'll see you next time.